In section 5.4, we're going to look at some different types of chemical reactions. So it's important to recognize that there are millions of possible chemical reactions, many of which can be generalized into a small number of reaction types. Now, as you progress into the organic and biochemistry portion of the GOB sequence, you will learn many reaction types. For our purposes, we're going to focus on 4 types of reactions. Combination reactions, which are sometimes referred to as composition reactions, decomposition reactions, combustion reactions, and oxidation reduction reactions, which are normally referred to as redox reactions. Redox reactions are quite involved, so we're going to do an entire section just on redox reactions. So it's important to recognize that classifying chemical reactions is important because it helps us recognize similarities between different reaction classes and also helps us to predict the products of a certain reaction. So the first type of reaction that we're going to learn about is combination reactions. And combination reactions are chemical reactions that make a single substance from 2 or more reactants. So you can recognize a combination reaction because it always has just the one product. And a classic combination reaction is the reaction between iron metal and oxygen gas to form Fe2O3 iron 3 oxide, otherwise known as rust. Another example of a combination reaction would be Fe2O3 reacting with sulfur trioxide to form iron 1 sulfite, Fe2SO3 solid. Decomposition reactions are kind of the reverse of a combination reaction. What happens in the decomposition reaction is that a single substance is converted into multiple products. So here we have the single substance sodium bicarbonate, and it decomposes to produce sodium carbonate, carbon dioxide, and liquid water. Here we have the single substance potassium chlorate, and it decomposes to form oxygen gas and potassium chloride solid. So easy to recognize because these kind of reactions only have the one reactant, but they have multiple products. It's the opposite of a combination reaction. Combustion reactions are very common, and combustion reactions are where a single substance, often a substance composed only of carbon and hydrogen, what we call a hydrocarbon, combines with molecular oxygen, O2, to form carbon dioxide and water. Generally, these will give off heat and light as a product as well. So a classic example would be propane, the kind of gas that you use to fire a barbecue, reacting with oxygen to form CO2, water, and a whole bunch of heat, which is why we can use it to cook a barbecue. Something like acetylene also provides an example of a combustion reaction. Acetylene is a gas used in welding torches, combines with oxygen to form CO2, gaseous water, and a whole bunch of heat. So that concludes section 5.4. We didn't talk about oxidation reduction reactions in that section because we're going to talk about those in section 5.5. Another important class of reactions are oxidation reduction reactions. These are generally described as being redox reactions because, well, it's quite a mouthful, isn't it? Oxidation reduction. In redox reactions, electrons are transferred from one reactant to another. The reactant that is losing electrons is said to undergo oxidation, and the reactant that is gaining electrons is said to undergo reduction. And we can use the little memory aid oil rig to remember this. oxidation is loss, reduction is gain. So a typical example of a redox reaction is the combustion of magnesium in oxygen, and this reaction is famous because it also produces a bright white light. Now we know that metals love to lose electrons and non-metals like oxygen love to gain electrons. So it's probably not surprising that in this reaction the electrons move from the magnesium to the oxygen. So often what we'll do when we're trying to figure out what's going on in a redox reaction is to break the reaction apart into two half equations. One that illustrates the oxidation or the loss of electrons, and the other that illustrates the gain of electrons or the reduction. So in this case, magnesium forms the magnesium 2+ ion by losing 2 electrons. In the reduction, half a unit of oxygen molecules gain 2 electrons to form a unit of oxide anions. Now, we say that the magnesium underwent oxidation and that the oxygen underwent reduction because the magnesium lost electrons and the oxygen gained electrons. There is another way of describing what is happening to each reactant. We can say that magnesium is functioning as the reducing agent because it provides the electrons that reduce the oxygen. And we can say that the oxygen is functioning as the oxidizing agent because it consumes 2 of magnesium's electrons. So that can be a little bit confusing. The reactant that is undergoing oxidation is the reducing agent, and the reactant that is undergoing reduction is the oxidizing agent, as it causes the other thing to become oxidized. So a classic redox reaction is the reaction between solid aluminum and solid iron 3 oxide to produce liquid iron, aluminum oxide, and a lot of heat. So let's have a look at that reaction now. And here it comes. So this is 6 pounds of a mixture of aluminum and iron 3 oxide that's referred to as thermite. And you can see that it produces a very large amount of heat as well as a large amount of liquid iron, which is that glowy orange substance that's accumulating at the bottom of those pile of bricks there. So this reaction is often used to weld railway tracks together because it makes liquid iron, and there's an image of the liquid iron at around about 3000 degrees Celsius. Okay. It's important to realize that in a redox reaction, oxidation and reduction occur simultaneously and can't occur without the other occurring as well. In the example that we gave, magnesium will not be oxidized unless oxygen is present, and oxygen will not be reduced unless the magnesium is present. For this reason, we say that the reactant that is oxidized is the reducing agent because it causes the other reactant to be reduced. And the reactant that is reduced is called the oxidizing agent because it causes the other reactant to be oxidized. So that's why we say that magnesium undergoes oxidation because it loses electrons, but it is the reducing agent. And similarly, O2 undergoes reduction, but it is the oxidizing agent. It's not too hard once you get used to the language. An important skill is to be able to identify what species is being reduced and what species is being oxidized in a redox reaction. So let's say we were given the balanced equation: zinc reacts with 2 hydrogen ions to form zinc 2+ and hydrogen gas. How we would identify what is being reduced and what is being oxidized is to break the reaction into 2 half reactions. So one of my half reactions will involve zinc and zinc 2+, and the other will involve hydrogen ions and H2. So I'm going to go ahead and write these guys out. Now, it's important to recognize that these half reactions at this point are not balanced for electrical charge. For example, in our first half reaction, on the left-hand side we have a total charge of 2, but on the right-hand side we have a total charge of +2. In our second reaction we have the opposite scenario. On the left we have a total charge of +2, and on the right we have a total charge of 0. To bring the charge into balance, what we need to do is add electrons to the more positive side until the charges are the same on both the left and on the right. So in the first case, we're going to add 2 electrons to the right-hand side because that was the more positive charge. And now you can see that we have 0 charge on both sides. In our second half reaction, we're going to add 2 electrons to the left-hand side because that was our more positive side, and now we have 0 charge on both sides. So what we want to see here, or what we want to recognize here, is that one reactant is losing electrons and the other reactant is gaining electrons. And if you recall, the reactant that is losing electrons is being oxidized, and the reactant that is gaining electrons is being reduced. Sometimes we're asked to write a balanced redox reaction given a description of the reaction. So in this case it says write and balance the redox reaction for zinc reacting with hydrogen ions in water to form gaseous hydrogen and zinc 2 ions. So the first thing that I want to do is write my balanced chemical equation. And there it is there, right? Zinc solid plus 2 hydrogen ions gives zinc 2+ ions and H2 gas. And I guess what I really got to remember here is that hydrogen is a diatomic element and that I'm going to need 2 hydrogen ions in order to balance the hydrogen atoms. So I can break this guy into 2 half reactions like we saw before. One for the zinc and its product, and one for the hydrogen ions and its product. So when I go ahead and do that, we see something interesting, which is important to recognize. When I add my 2 half reactions together, if I cancel out things that appear on opposite sides of the arrow, I get my overall reaction. And that's a really important concept. When you add the 2 half reactions together, you get the overall reaction and all of the electrons will cancel out. Okay, just to kind of reiterate a point, we identified previously that the zinc is undergoing oxidation because it is losing electrons. Therefore, we describe the zinc as the reducing agent. The hydrogen ions are undergoing reduction because they are gaining electrons, and therefore the oxidizing agent is the hydrogen ions. So one way of tackling a problem like this, where it says write and balance a redox reaction, is to identify the pairs of reactants and products. Then you can write the two half reactions and then add those two half reactions together, cancelling the electrons to give you the overall balanced redox reaction. So we'll illustrate an example of that now. So this problem from the book reads, write and balance the redox reaction that has calcium ions and potassium metal as reactants, and calcium metal and potassium ions as products. Identify the substance oxidized, the substance reduced, the reducing agent, and the reducing agent, but I think that's meant to be oxidizing agent. We'll deal with that in a second. So first of all, we want to identify our reactants. Our first reactant is calcium ions. So calcium's in group 2A. So these are going to be Ca2+ ions. Our second reactant is potassium metal. So potassium is not a diatomic element, so that's just going to be K for potassium. So that's our two reactants. We want to leave a space and then put our arrow, just in case we need to add some extra stuff in. It says the products are calcium metal and potassium ions. So calcium metal, calcium is not a diatomic element, so it's just going to be Ca. And then potassium ions, they're going to have a single positive charge because potassium's in group 1A. So now we need to figure out how many electrons are involved and what reactant is losing or gaining electrons. And to do this, you want to look at the total charge on either side of your arrow. So the total charge on the right in my first half reaction is 0, and the total charge on the left is +2. For my second reaction, the total charge on the right is +1, and the total charge on the left is 0. Having done that, you want to add in electrons to the more positive side until the charge is the same on both sides. So here I want to get +1 down to 0, so I'll be needing to add in 1 electron. And up here I want to get +2 to 0, so I'll be needing to add in 2 electrons. So at this point, we have our half equations looking pretty good. The charges are all figured out. We have the correct number of electrons on either side of our arrow. There's one slight problem though, and that slight problem is that our first step consumes 2 electrons, but our second step only produces 1 electron. So what we're going to want to do now is multiply everything in our second step by 2 in order to have the correct number of electrons involved. And there we are. we have a situation where the electrons that are consumed in the first step equal in number the electrons that are being produced in the second step. So at this point, I can add these two equations together, cancelling out the electrons that appear on opposite sides of the arrow. So the reaction will be Ca2 plus 2 potassiums gives 1 calcium and 2 potassium ions. So I've got my balanced equation, but I also need to identify what is being oxidized. What is the reducing agent? What is being reduced? And what is the oxidizing agent? So, oxidation is loss. So, it is the potassium metal that is losing electrons and being oxidized, and that also makes it the reducing agent. Reduction is gain, and it is the calcium ions that are gaining electrons. And so that means that the calcium ions are being reduced, and whatever is reduced is the oxidizing agent. And like I said, I think that was an error there and that it was meant to read oxidizing agent. Okay, that concludes this section on redox reactions. There's plenty of questions in the book to practice. This also concludes chapter 5.